This is going to be the first part of 4 or 5. We'll hit the second part in the next chapter. By the way, just looking at the date now of when this was recorded in American history, this is Friday, April 17th, 2020, kind of around 10:51, 11 o'clock. And today, the U.S. is going to breach 700,000 cases of COVID-19. So if you're watching this sometime in the future, this is where we are right now. So in any case, we learned a couple of things in the past, that if you have a function defined as the product of two functions, f of x times g of x, that the derivative of the product of two functions by product rule is the first function times the derivative of the second plus the second function times the derivative of the first. So that's going to operate as a little bit of review of where we are. We also learned something called the quotient rule, that if I have a function defined as the quotient of two different functions, that its derivative, h prime of x, is equal to low d high minus high d low over low low, low meaning the denominator times the derivative of the numerator, minus the numerator times the derivative of the denominator over the denominator function squared. That's an easy way to combine a derivative into a single rational expression. And then the final one that we did was what was called chain rule. And I'm going to write that down because what we are doing today is the reverse of chain rule. Chain rule operates when you have a function contained within another function. So this is the case of f of g of x. This is basically any time that you have a function inside and then something else is being done to it. Its derivative by chain rule was the derivative of the inner function g prime of x times the derivative of the outer function with the same inner function applied, f prime of g of x. So what we're going to do now is we're going to take something that's in this form and we're going to do its indefinite integral. I'm going to take the integral of f prime of g of x times g prime of x, which is just the same thing. I just switched the order of the two of them, but that's exactly the same thing. And we're going to do this with respect to x. So the process that we're going to use is we're going to let a variable u, this is actually the reason why all those years you had me, I used u as my substituting variable. It really came down to this thing. We're going to let u equal this. U equals the inner function, which is going to be g of x. And then I'm going to take the derivative u prime, but rather than u prime, we're going to say du is equal to the derivative of g of x is g prime of x dx. By chain rule, I take the derivative of this inner x and I get dx with that. So this is going to be the key here. We're going to have u equals g of x and du is g prime of x times dx. Now we're going to do lots of substitutions. In fact, we're going to replace x with u everywhere. And everywhere meaning there's just a few replacements that we are making now that we've done the substitution. For one, let's start with this thing here. This means that dx was equal to du over g prime of x. So that's going to go right in here. So I get this du over g prime of x. I'm also going to replace this thing here with u. I get f prime of u. And I'm not going to replace g prime of x with anything because, as you can see, that's going to actually cancel with this denominator here. So I get the integral of f prime of u du, and the integral of f prime of u du is just f of u. So, plus constant, we should say. So going back up, that's kind of where we started off with, and now we're going to go back to x's. And I know that u is equal to g of x, so this is just f of g of x plus c. So what I've done is really do this same process of taking a derivative. I've just completely gone in reverse and gone from the right side of this back to this left side, back to this, this composition of functions. So if that seems confusing, that's because I'm doing this completely with variables now. But I want to show how this is going to work with non-variable expressions. What I'm going to try to convince you of is that you are going to use this process a lot. I mean, this is one of the bigger aspects of calculus you're learning today, because you're going to use substitution quite a bit. This is one of the bigger picture things that we ever do. So we have two ways to integrate this. One of them is to multiply it all out, but I'm not going to do that. I'm going to start with a simpler example to illustrate a concept. Nick Franklin always says that he wants to start using simple examples to illustrate a concept, even though there might be a simpler way, another way to do it. So we're going to start with the inner function. U is equal to 2x plus 1. And then I'm going to take a derivative. Du is, the derivative is 2, but I'm going to put a dx. And then I'm going to, off to the right, solve this for dx. So I get dx is equal to du over 2. Now I get the original that I'm going to rewrite everything in terms of u. So this was u squared, and I said dx was equal to du over 2. I like pulling out constant multipliers, and we have a 1/2 factor that I could factor out and just get 1/2 u squared du. What I've done is I've made a more complicated problem become a simpler problem, the integral of u squared. And the integral of u squared is u cubed over 3 plus constant. So final steps are to multiply the 1/2 times the 1/3, and then to express the u cubed that's sitting there, to put that back in terms of x's. So this would be 2x plus 1 cubed plus constant. Two things people forget. Two things easy to forget. The first thing is the c. So don't forget the c. The second is to rewrite in terms of x, not u. So please don't do those two things. I typically, in the school year, take off a point for each of those, and there are some that just mess it up in every problem. I have to take off a point in every problem because then they never do it again. Okay, number 2. This is a classic case of where u substitution is used to do this integral. Because what you see is the integrand, which means the thing you're taking the integral of, is composed of a product. And one of those things that you're multiplying by happens to be the derivative of the thing inside the radical, what we call the radicand. So if I let u equal the radicand, we get u equals x cubed plus 1, then du is 3x squared dx. When I rewrite this, I rewrite it as dx equals du over 3x squared. What I'm going to notice is that that x squared in the denominator is going to divide out the x squared that happens to be multiplying by right up here. So because this is still early, let's write this all out. Integral x squared, radical, I'm replacing the radicand with u, and I'm replacing du with, this should be a dx right here. I'm replacing dx with du over 3x squared. The x squareds divide out. The divide by 3 we can pull out as a 1/3, and I'm going to rewrite this as 1/3 integral u to the 1/2 du. More complicated problem just became a simpler problem. To integrate u to the 1/2, that's the same thing as u to the 3/2 divided by 3/2 plus c, which is the same thing as when you divide by 3/2, that's times 2/3 times u to the 3/2 plus c. And now let's put everything back in terms of x's. The 2/3 times 1/3 becomes 2/9. We get the u is x cubed plus 1 raised to the 3/2 power plus constant. You can, of course, always check this by taking the derivative, but I think you'd be able to see that the derivative of the x cubed plus 1 is going to become a 3x squared, which is eventually going to give you that x squared that you see. Okay, next example. Let's change color, something a little bit lighter. Okay. The integral of sine of 6x dx. This is a much easier example of a u substitution. I'm just going to let u equal 6x, and then I'm going to let du equal 6 dx. And that means that dx was equal to du divided by 6. So when I substitute this back in, I get the integral of sine of u times du, and then the divide by 6 comes out as a 1/6. I'm going to start taking those constant multipliers and just pulling them out right away. So really all we have is the integral of sine, which is negative cosine, plus a constant. And now I'm just going to clean things up. We're going to take the negative 1/6 cosine. U was actually equal to 6x, and then plus constant. And I think if you check this by taking a derivative, you'd see that this derivative would become the original problem. It would become sine of 6x. Okay, number 4, integral of 2 secant squared x times tangent of x plus 3 squared dx. Looks so much more complicated than it actually is. Because if you let, let's do this, if you let u equal this thing, and you take that 2 and move it out in front, we can just do a couple of things here at the same time. U is equal to the tangent of x plus 3. One of the first questions people tend to ask when they do this is, how do you know what u is going to be equal to? And one of the ways you know that is you always want it to be equal to the inner function of something that's happening to it. So we see that we have something squared. Well, let's let u equal that something. And sort of like very competent chess players, you want to look ahead just a step and realize that the derivative of this is going to be equal to the secant squared that you need to cancel right there. So that's going to take care of that secant squared x. Don't forget your dx. Because dx is going to be equal to du divided by secant squared x. I like these problems a lot because they tend to work themselves out very nicely. You have that 2 that just moves out in front. You get the integral. The du that you're substituting in here, the secant is going to cancel with that secant, so that's gone and you don't have to worry about it. Furthermore, you just have a u squared du. And that's all this problem is. This whole complicated thing you just saw right here just comes down to 2 times the integral of something squared, which is one of the more simpler integrals you've done. 2u cubed over 3 plus constant. You get a 2/3. The u that you were cubing was just the tangent of x plus 3 cubed, and then plus constant. And that's it. Let's do some more practice on this. The sine squared of 3x cosine of 3x dx. Here you have to get a little clever, but probably the first thing I'm going to do is just do the integral of sine of 3x quantity squared cosine of 3x. This is a rewrite to see what's really going on. And what makes sense? Do I let u equal this thing, or do I let u equal this thing? If I let u equal the sine of 3x, it's going to cancel out the cosine of 3x quite nicely. So u is equal to the sine of 3x. Du by chain rule would be 3 times the cosine of 3x dx, which means that dx is equal to du divided by 3 times the cosine of 3x. So when I substitute this back in to dx, the cosine of 3x is going to cancel. The 1/3 is going to factor out as a constant multiplier. I'm going to get the integral of, let's see, u is equal to 3x, or sine 3x. So I get the integral of u squared du. And again, we get 1/3 u cubed over 3 plus a constant. And that means that this ends up being 1/9. U was sine of 3x, so this is the sine cubed of 3x plus constant. Now I want to show you a case of where you can't use this. So let's say that I have the integral of x squared plus 1 cubed dx. I can't use this because if I let u equal x squared plus 1, my du is 2x dx, which doesn't cancel anything out. So that means that this strategy is out. We're going to have an entire unit in Chapter 8 on the art of integration, where we combine many, many, many methods. But the only method you'd have here would be to expand this, meaning multiply this out. Well, how do you multiply out something cubed? Let's remember Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, where every number comes from the sum of the ones on the outer two. And this lists the coefficients of all these different values. So that means that we'd have a 1 in front of our first term, and our first term would be x squared cubed. That would be an x to the 6th. Then our next one would be plus 3x to the 4th, then plus 3x squared, and then plus 1. That's where our 1, 3, 3, 1 comes from. And if I integrated this dx, then I would just get x to the 7th over 7 plus 3x to the 5th over 5 plus x cubed plus x, and then plus a constant. And that's about as good as we can go with that one. I wouldn't want you to add those with the least common denominator of 35 right now. Okay, another problem that comes into play that you don't use it for is something like this. The integral from -3 to 3 of root 9 minus x squared dx. First of all, this is a definite integral, so this is asking for area. Second, this definite integral is one that you know. We are not going to do u equals 9 minus x squared for the same reason that my du would be equal to -2x dx, and that doesn't cancel anything. But this shape happens to be a semicircle centered at 0, 0 with a radius of 3. So if I know that, and I know that the integral is from -3 to 3, I'm asking for this area. Furthermore, I also know that a more efficient way to write that integral would be the integral from 0 to 3 multiplied by 2, because that is just the area of this thing. So given that, it's not essential that you write it that way, but it's useful to know that we tend to want to write things as simply as possible, or as more efficiently as possible. Twice the area of a quarter circle. This quarter circle would be 1/4 pi times the radius squared, which would give me 2 times 9 pi over 4, which is equal to 9 pi over 2. And that would be what the integral value is equal to. One other point I want to make to you while I'm on this idea of a circle is that every one of you know that the circle formula is equal to pi times the radius squared. But you also know my propensity for the number tau, and why I think that's so much more valuable, that if this pi was equal to tau, it'd be equal to tau over 2, because pi is half of tau. And your area formula for a circle would be 1/2 tau r squared. Those of you in physics recognize 1/2 mv squared or 1/2 at squared, and kind of this way that this kind of 1/2 something times something else squared tends to creep up a lot in math and science. This is the area of a circle, which seems more complicated, but the area of a sector is equal to 1/2 theta r squared, where this tau is now replaced with whatever angle, and that's the area of the sector of a circle. That would have been so much easier to remember if we had used tau from the get-go. So, okay, side note aside, let's get down to one more problem, and this is going to be one that's a little bit more challenging. Integral from of x minus 2 times root x plus 1. Now, we always said we wanted to make u equal to the thing that is more complicated, or something more complicated is happening to. So I'm going to let u equal x plus 1. du is just dx. Du is 1 dx. So why are we doing this? We're doing it because my replacement thus far could be done to where I can't cancel out the x minus 2, but I can make this a root u, and I can make the dx be equal to du. So what's left is this x minus 2. Well, I can actually replace that with u if I take this and make x equal to u minus 1. we're going to put that into here and completely substitute this. U minus 1 minus 2 happens to be U minus 3. Why can we do that, or why is that helpful? Because I can multiply those and make this expression become the integral of U minus 3 U to the 1/2 du, and then this is the same thing as the integral of U to the, okay, so U to the 1 times U to the 1/2 is U to the 3/2 minus 3U to the 1/2 du, and it's written in a polynomial form, which I can now integrate and make this 2/5 U to the 5/2 minus, so this becomes 3/2, which means times 2/3. And if I multiply it by 2/3, I get a 2 U to the 3/2 plus C. This is extremely valuable because now we have an integral, and all I have to do is replace the U back completely. 2/5 U to the 5/2, which U was equal to x plus 1 to the 5/2 minus 2 times x plus 1 to the 3/2 plus constant. And this would be sufficient. I want to show you how you can simplify this a little bit more if you can. And you should have some practice with this algebraic manipulation we're about to do. What I'm going to do is I'm going to factor out what I can, meaning we have a 2 in both of these and a 5 in one of them. I'm going to pull out a 2/5, and I'm going to pull out an x plus 1 to the 3/2 out of these two. I can't pull it out of the constant, but I can pull it out the other two. Dividing out a 2/5 has the same effect as multiplying by 5/2, so that goes away in the first one. And when I divided x plus 1 to the 3/2, it's like subtracting an exponent. I just get x plus 1 to the 1 power. With this 2 here, I'd also multiply that by 5/2. This becomes a minus 5, and I factor that out completely. And then I just get a plus constant off to the side. So another alternative way to write this would be 2/5 x minus 1 to the 3/2 times x minus 1 minus 5, which would just be x minus 4, and then plus constant. So I would be very impressed if you can go from here to here on some of these problems. It's not completely required, but it's helpful to do. Okay, that's it.